My name is Ruben. I work at Twitter on Finagle, which is our RPC library that we use extensively across our microservices. It encodes tons of best practices from the industry and things that we've learned for doing RPC at scale. And as Emil said, today I'm going to focus on specifically a client-side load balancing algorithm that we use within Finagle. And this kind of picks up pretty squarely where Morelli and Laura left off with layer 7 load balancing. So why do we want to do layer 7 load balancing? So we're talking about load balancing in the context of microservices where there's hundreds or thousands of replicas or instances. And in order to safely make use of this aggregate capacity, we need to front them with load balancers. Now that all the requests to our service, to our respective services going through a load balancer represents an ideal location to route around failures of these replicas when they inevitably happen. Let's break down some of the terms that we use to describe our load balancers. We say they're non-cooperative, which means there's multiple load balancers, each making decisions independently. And this allows us to maintain this distributed architecture without expensive cooperation. We say that they're client-side, which means that they're embedded on the client, and this allows us to operate with fewer layers of infrastructure. And when we talk about load balancing, we're talking about load balancing over both sessions and requests. We care about session distribution, but we mainly measure the efficacy of our load balancers based on request distribution because it's a more accurate proxy of resource utilization. So let's take a look at an example topology. Here we have service A talking to service B. Each instance of service A has an embedded load balancer, and we have an equal session distribution on service B because each load balancer opens one session to each instance in service B. So given this topology, how do we balance requests? We use a strategy that we call P2C, and this is based on the seminal paper from Michael Mitzenmacher called The Power of Two Choices. And how this works is as follows. For every request that comes into a load balancer, we select two instances to compare, uniformly and randomly. Of those two, we compare them based on the least loaded, and then we route the requests to the one that's least loaded. This has a few nice properties that I want to highlight. First, the P2C paper tells us, or the Power Two Choices paper tells us that if we employ this random process, we actually arrive at a load distribution that is exponentially better than random. So in practice, we see fair request distribution when services have homogeneous replicas. It's also really efficient. We don't have to synchronize on expensive data structures. We can do this all in constant time as well. And more subtle point that I want to highlight here is that this algorithm decouples selection and comparison. So step 1, we select randomly, knows nothing about the load. Then step 2, we actually compare the load. And this is really powerful. We'll see how we make use of this later on. What about per session load balancing? Well, we saw in the diagram, it's just a mesh network. We don't do anything fancy, at least yet. And this has a lot of negative consequences for resource utilization. There's inherent cost of a session. On top of that, we have to do health checking on each session to make sure that we don't compromise success rate of a service by routing to an unhealthy instance. And just to add insult to injury there, every load balancer has to do the same thing because they're non-cooperative. So when one instance is bad, every load balancer has to discover it independently. There's no isolation there. And finally, when you're using these load metrics that are actually embedded on the client, if you don't have enough concurrency on the client, you end up having these low fidelity metrics that when you compare them, they don't really give you a lot of meaningful data. So you actually have to increase the concurrency per session so the load balancer can do relatively meaningful comparisons. So this begs the question of how can we reduce the number of sessions to sort of combat some of these problems. And our first attempt at a solution here was something we called random aperture. And an aperture is just a window over your service that the load balancer maintains, and it tries to maintain the smallest window such that there's one active request across every session. And it does so with the feedback controller, and the feedback controller effectively has a set point of one request. So it can dynamically grow or shrink the aperture. And then finally, the process of selecting which sessions go inside the aperture is random. So this may look something like this. So the same service topology we were looking at, we have service A talking to service B. So each load balancer in service A has an aperture of 3. The idea here is that we converge on a uniform aperture because service A is also being load balanced too. So this looks good, except for this glaring problem that we've created hot and cold spots on service B. It's kind of hard to appreciate the magnitude of this problem from small examples like this. And at the risk of making some of you compulsively check your on-call pagers, this is what happened when we deployed the set scale. So what are we looking at here? We're looking at a time series graph. This is RPS per server over time. And we see this inflection point where the clients talking to the service have deployed random aperture. And it's basically just chaos, utter chaos. We have this wide distribution of request load, makes it really hard for service owners and operators to reason about capacity planning, overload scenarios, and just in general leaves a lot of resources on the table. Fortunately, because random is statistical, we have all the statistical tools at our disposal to reason about this. Turns out the process that we use to assign sessions to apertures can be closely modeled by a binomial distribution. And we can minimize this banding that we saw in the previous graph by expanding our aperture, but we can't completely remove it unless we actually open the aperture completely. So armed with this knowledge, we decided to set up an internal wiki page that would point service owners and operators to how to use the binomial distribution to configure their apertures. And in retrospect, this was a really bad idea. Don't do this. Not because it didn't work. Here's another service going from pure vanilla random aperture to a well-configured aperture. And we see that it has a much more manageable request distribution. We still see banding, not as bad as on the left side. But the core issue here is that we are distributing and pushing this configuration burden on our service owners, and it just proliferates poor configuration. This is configuration that will go stale. Over time, it will just converge on poorly configured infrastructure. Let me just grab my water from here. Okay. So how can we improve on this? So a key piece of insight was to move to ring topology. And what we've done here is we've taken the same services that we've been looking at, and we simply mapped them to a ring. Each respective instance of a service gets a specific position on a ring, a discrete coordinate. And then the instances of a service are equidistant on a given ring. And this looks very similar to consistent hashing. The key difference here is that we aren't using hashing. We're simply mapping the instances onto the ring based on some knowledge from our service discovery system, which is basically how many instances are there and what's the instance ID. This allows us to have this uniform distribution on a ring. So independently, these two rings don't bias much, but because the rings actually share the same domain, we can compose them. So here we have the two rings composed, and this allows service A to derive a unique ordering of service B. So for example, instance 0 of service A can walk the ring clockwise and derive the ordering 0, 1, 2, 3, 4, 5, 6. Instance 1 can do the same and derive the ordering 3, 4, 5, 6, 0, 1, 2, and so on. Now that we have this unique ordering, we can expand our aperture over it. So on the left-hand side, you see that each client is expanding its aperture, converging on a size of 3. And this gives us the histogram on the right-hand side. And this looks good aside from the fact that we have these off by 1s. So what's happening there? It's a lot more pronounced when we start composing more rings together. So here we introduce service C. Service C knows nothing about service A. They're both talking to service B. And we start to see this visual crowding on the ring. And if we look at the histograms on the left-hand side, we see now we have hot and cold spots again. So 5 is represented 4 times across all the apertures, and 1 is only represented twice. This can be even more pronounced when we're measuring request load, not just session distribution. So to combat this, what we did was we moved to continuous coordinates. So services now fully occupy the domain, and an instance effectively just takes a slice of the domain and it can map to the service that it's talking to. So this looks good so long as we can actually respect this representation when we're load balancing. This is where P2C really comes in handy. So each load balancer can now pick 2 coordinates within its range and map 2 discrete coordinates onto service B, for example, in this case. And because we're using this random process, we inherently respect these fractional load boundaries. A wall of code. Let's go back there. I want to walk through the mechanics because I think it'll help illustrate what's going on here. So on the right-hand side, I've illustrated the same ring. We're looking at one load balancer that has a slice. And what I've done here is I've annotated what proportion of the slice of service B fits within this range. So instance 4 gets 2/3 the load of instance 3, and 2 gets 2/3 the load of instance 3 as well. So how this works is each load balancer knows about its offset and width. And again, it only needs to know about its offset and width. It doesn't need to know about all the other peers. And then we pick 2. And I've omitted the implementation details of pick 2, but it's pretty straightforward here. We're just computing the intersection between the rings. So this gives us indices A and B. So what we expect with this diagram, the result of A and B is, again, 4 and 2 to be picked 2/3 as often as 3. Then we map those indices to nodes. Nodes simply give us more metadata about an instance, so things like status and load. Then on lines 13 and 14, we inspect the status and we compare it. And this allows us to do the routing around that we originally talked about. So status sort of rolls up all of the circuit breakers within Finagle into one value that's comparable. And then on 18 and 19, we actually compute this weight for the respective A and B that we chose. And then we have to do this normalization of load on line 22. And the reason for this is we know, so let's take the example that we chose 4 and 3. We know that 4 is picked 2/3 as often as 3, so it will just naturally have less load than 3. In order to not bias towards it when we're comparing the load, we actually need to normalize it by its weight. So we want to set up this inversely proportional relationship between weight and load. And that's it. This is sort of the crux of the algorithm on one slide. Again, omitting pick 2, but everything else is pretty straightforward. It's worth looking at this across multiple services that know nothing of each other. So again, here's service A, another service C. They're both talking to B. Visually clear that we're loading B fully and evenly. So the continuous coordinate model gives us a fair request distribution across distinct service rings. It still maintains this distributed property. We have very light coordination to get this metadata that allows us to construct the rings, and this simply piggybacks on our service discovery system. So we need to know, for example, instance ID and how many of a particular service there are. And then it also maintains fewer sessions. So we haven't talked about exactly how the aperture is computed, but it's implied that it's sort of split evenly across this ring. But it's not fixed. So here's an example where, looking at the same services, we want to add a constraint where we want to have a minimum aperture size. So for example, before we were talking to 3 services, actually 2 and a third, we say we want to have at least 4 services. And you can have these constraints, for example, for resiliency. You want to make sure that you don't wipe out your entire aperture, or the probability of wiping it out is a lot less than normal. And the way to do this is simply have to wrap around the ring a whole number of times. So in this case, we wrap around twice, giving each instance of A 4 and 2/3 of service A. Sorry, service B rather. Just a short note on the resiliency of this model. We inherit a lot of the benefits that consistent hashing does, simply because we're using a similar ring representation. So we have this property of minimal disruption. And this diagram shows when we, for example, 6 goes away, we simply close the ring and we have minimal movement for the other nodes. And this is really important because we want to make sure we minimize session churn. And then we've built some other resiliency features into this implementation. We've built in this property of entropy. Now that everything is completely deterministic, we want to make sure we avoid what Laura was talking about earlier today, which is thundering herd. We want to make sure that, for example, if you have rings that have similar looking apertures, then, for example, let's say one node goes away, all the load routes around those, or not necessarily goes away, but becomes a zombie. All the nodes sort of all their load routes around those nodes in a synchronized fashion. And then you basically have this coordinated DNS attack. So what we do is we shuffle every outer ring's view of the inner ring is shuffled in a deterministic way. We also have this property where we coalesce updates. So let's say we receive tons of updates from our service discovery system. We can buffer them for a short period, and we can say, hey, we don't need to actually flush these one by one. We can inspect them and say, this add can be coalesced with this remove, for example. And then we use this pure size heuristic mainly to combat rolling restarts. So when you restart clusters in batches, you're sort of wiping out an entire aperture. As you an entire ring, as you rebuild that, if you rebuild it slowly, what happens is you're just moving nodes around slowly to their final positions. So if you can sort of guess their final position, it helps a lot in reducing session churn. And we use some heuristics based on our service discovery system to say, for example, say you reboot 100 nodes and you know there's 100 nodes in that system based on the fact that 99 comes up. So this allows us, again, to place nodes where they belong earlier on. So we've been using this in production for a couple of years now, and we've had some great results that I want to highlight. So here's a service going from a well-configured aperture to this well-configured random aperture to this new version, the ring-based model. And what we see here is a 78% reduction in standard deviation for requests per second. So these are the same graphs. One of them is aggregate requests per second, measured as relative standard deviation. The bottom graph is the raw data, the raw requests per second across servers. And here's that same service. Now we're measuring how many connections it has. So we have a 91% drop in aggregate connections across that link. So we go from 280K to 25K. Some second order results that we've seen from this, or that our customers have reported, we see 75% fewer failures in this specific service, 20% reduction in latency at P39, 20 to 25% less CPU used, and total garbage collection time cut in half. Lots of these are second order results from just the vast reduction in sessions and connections, and also the new isolation model that we're getting from this. So this is the work of many. Lots of people have contributed to this and shaped the idea over time. This is 95% of this is open source on the Finagle project. If you're interested in diving deeper into the code snippet that we looked at, feel free to jump on GitHub and check that out. And I think we should have some time for questions. Cool. I think we can just walk up to the mic.
Yeah, so I was curious about how you handle the in-between, right? So like if you're moving to client-based load balancing and you're going service by service, I feel like you're gonna have this this kind of mixed mode, and wasn't sure whether you had any strategies for handling that.
So Twitter has historically used client-side load balancing since the inception of Finagle. But there are tricky things with even upgrade, like if you're not set up as an organization to manage client-side load balancing, like Murali and Laura were saying, where you control your clients very well, that can be tricky. But we have all sorts of things like toggles, where we can ramp these things up slowly and in a controlled fashion. But I don't have any sort of tips off the top of my head for going from a different architecture to client-side. Mm-hmm.
I noticed there that in your graph where you showed transitioning from the well-balanced binomial distribution to your ring architecture, that you had quite a bit of noise during that transition period. And it raised the question for me, what are you doing, or do you really concern yourself too much with how you deal with bad neighbors or badly behaved clients within your architecture, and how you would design this algorithm to support that? That's
a great question. So I briefly touched on resiliency. The transition period, the noise that you're looking at, is probably the worst it'll ever be. Simply because you have these random nodes, these nodes that are going from random to something more deterministic. So we have things like, let's see, let me, off the top of my head, some of the resiliency features that I mentioned was, I guess, the minimal disruption feature where the rings, when everyone is on this new system, sort of transitioning is hard, but when everyone is on this new system, we should sort of inherit the minimal disruption that I was referring to earlier. Cool, thank you guys.
Let's give Ruben a round of applause.